Good afternoon. My name is Micah Schur. On behalf of the SaTC Technical Program Committee, it's my pleasure to introduce this afternoon's keynote speaker, Nick Sullivan. Nick is the head of research and cryptography at Cloudflare, where he leads research efforts in security and privacy, cryptography, and internet measurement. Nick has been active in helping roll out cryptographic advances at scale, including TLS 1.3, to Cloudflare's 20 million internet properties. And I double-checked, it really says 20 million. He is also active in Cloudflare's deployment of encrypted DNS. His work, undeniably, has a real-world impact. He is a regular fixture in the IETF community, helping transition research ideas into practice and in a way that scales to tens of millions of users and sites. Prior to helping encrypt the web at Cloudflare, he worked at Symantec and Apple as, according to his website, a mathematician. Today, he's going to share his vision on how to provide security and privacy at super large scale by encrypting the internet. Please join me in welcoming him.
All right, thanks, Micah. So yes, I'm Nick Sullivan. I'm the head of research. Oh, sound adjustment. Yeah, so head of research and cryptography at Cloudflare. And my job is to help build a better internet. I'm really honored to be here representing industry to this extremely esteemed audience. And before I go into this talk, and I'm going to be sharing some stories during this talk, I'd like to highlight Cloudflare's approach to research, how we think about research, and it really comes down to three things. First, getting your hands dirty, and then secondly, getting a bit of distance to see the big picture, and third, working together with other people, both in the industry and academia. And this means internships, partnerships. We've had a lot of people come to Cloudflare to work on research projects, and we've worked externally with a bunch of other people. So this talk is going to be focused on three different parts. Well, as I mentioned, it's about encrypting the internet, but encrypting the internet at Cloudflare, so internal to Cloudflare, for Cloudflare's customers, which we'll learn are pretty numerous, and then on the internet at large. And so building a better internet starts with our approach to research and the needs of these 20 million internet properties we serve and the internet community at large. And this topic is going to be about the rapid expansion of encryption technology on the internet over the last 5 or so years. And I'm going to explore some of the technical challenges and inside stories that help shape what happened. We're going to look at problems, research angles, results, and new questions. And so you may ask, who is Cloudflare? This is maybe most people's exposure to Cloudflare is this error screen. You've probably seen it. There's also this wonderful, I guess, not marketing stunt, but we use lava lamps to help generate random numbers in Cloudflare's office. And this has really led to a public perception of what the company does. And so I'm going to show a short video. This was surprising to us when we saw it, but this was from a show that showed Globium Technologies. This is what it looks like. I didn't make that video, obviously, but so this is what it looks like, and this is what Cloudflare looks like. So you can maybe connect the dots and sort of figure out what it does. But as far as I know, you can't hide a Trojan horse inside the encryption engine. In any case. What is Cloudflare and what they do? I don't want this to be a vendor pitch or anything, but I want to explain Cloudflare's scale and scope and why it's relevant to encrypting the internet and be able to make real progress on this issue. So Cloudflare works, the main product of Cloudflare works as a reverse proxy. So you have a user trying to connect to a website. It goes to Cloudflare first. If there's something malicious, whether it's some sort of SQL injection or a malicious attack or a DDoS, Cloudflare will block it and sort of send everything through to the origin server for the website itself. If something's cached, it can be served directly from Cloudflare, and this helps speed up and secure internet properties. And the reason that this really helps is that Cloudflare is globally distributed, and you might not be able to see here, but there's a globe behind that. And Cloudflare's network is actually, it's really massive. 10% of all Fortune 1000 companies pay for some Cloudflare service. As we mentioned, there's 20+ million sites, and it's served out of 190 cities or so worldwide. We do millions of requests per second. And the types of customers are global financial services, public sector, technology, e-commerce. The reason there's so many customers for Cloudflare is that there's a high-end enterprise service as well as a free paid service. You may recognize things like Eurovision, the UK government, Uber, HackerOne, IBM, the IETF itself, Fitbit. And so given that, and given that Cloudflare's scale and sort of importance to the internet, let's take a little bit of a step back into the past, and specifically to when Cloudflare's logo looked kind of like this, and before I joined, and let's kind of explore one of these questions. So I previously had worked at Apple and was going to move over to Cloudflare in July 2013. In terms of internet security and the way that people thought about information traveling over the internet, there was one big sort of event here, and I think you know whose face is going to show up here. But yeah, Edward Snowden's revelations really changed the way that industry thought about encryption and thought about the importance of sending information over the internet in very concrete ways. And so previously and currently, a lot of times we think about data privacy as information shared between a user and a service, and you have a privacy policy that limits third parties, insiders, whatever, from sharing the information that the user has given to the service. And well, with Snowden's revelations, there's one additional party to this service, but this wasn't really the key point and the key salient point that helped push this idea of fully encrypting the internet or moving the internet encryption forward. That sort of goes to the idea of how this information is transferred from the user to the server itself. There are various intermediaries. You have ISPs. The ISPs use transits. You may be connecting through a local network, say the Hilton network or a coffee shop, and the service provider may be operating on a cloud of some sort. And so privacy is about determining who has access to your information, when and where. And one tool that can be used to help limit this is the end-to-end principle, is encryption. So if you have the ability to know which two endpoints share a key, you can transfer information over any sort of network and be assured that the content of the information is not shared. So this is necessary but not sufficient for privacy. And so one very effective tool for doing this is transport layer encryption protocols. And so if you encrypt this, then the coffee shop, the ISP, the transit, the cloud provider, and potentially any other people listening, which is a very, in 2013, became a very well-known and very real determinant of who could listen on this traffic. And with encryption, this no longer becomes a case. And so if we step back to 2014 and look at what the web looked like and popular websites, all of these sites were using unencrypted technology, HTTP, at the time. And this may seem ridiculous to us right now in 2019, but yes, Wikipedia was not encrypted, and neither was Amazon.com. And so let's put a pin in this for now, this idea of this lack of encryption, because around the time when I joined Cloudflare, we had more pressing problems. So before we go into this, I guess you can't see the other two, but it says, at Cloudflare for customers on the internet. There was another slide that's maybe notorious that was going around at the time, and this is the SSL added and removed here with the little smiley face. But the key insight here is that you can use SSL TLS to connect people end-to-end, user to the termination service of TLS, and then you have to use encryption on the back end as well. And if not, then potentially this information can be revealed. So at the time I joined Cloudflare, this is taken from the team page, and they still sort of list people chronologically from joining. That's me right there. So to say that we were a scrappy company is sort of an understatement. And we did have over 2 million web properties using the service at the time. So it was a very different world, and we were very short on resources. And one of the main problems or the first problem I was brought in to solve was this idea of moving settings from a central database to this widely distributed network across the world. We had some internal tools here that this topology doesn't really matter, but essentially sending data, including the private keys of all the websites. As I mentioned, Cloudflare sits in front of websites, and in order to do the transport layer encryption, it needs a copy of the private keys. And so, as a problem statement, stepping into this is, Google wasn't able to do this, didn't have encryption at the time. You could barely imagine a small company would have this type of security. But given the constraints here, the problems were the internet itself is untrusted. The network itself is geographically dispersed and growing, and so how do we actually send our data securely and efficiently with no additional complications? And so the old-fashioned idea here is to use something called IPsec, but given the way that our network was constructed and deployed and how the cost was structured, this was completely unfeasible. It required separate hardware, and Cloudflare was building its service to be one router, one switch, and a bunch of servers that each did everything identically. So this wasn't something that was going to work. So there are other ideas that we were exploring. First, there's service-to-service TLS. This is something that is common now, but was not common at that time. And then there's the idea of end-to-end encryption, and then additional things we could look into in terms of hardware and attestation. But again, resources were very constrained at this time. So the first thing that we came up with in order to solve this and not have to change all of this software to support TLS SSL, although we eventually did so, was to build an end-to-end encryption tool. So the data before even being inserted into the database was encrypted, and it was sent through this replication service that has no idea that the data was encrypted, and eventually the service at the very end of it, which in our case was Nginx, was the only service that was actually able to decrypt the private key, and then it could use it. And so in order to keep this locked down from the rest of the company and insiders, we built an implementation of the so-called two-man rule or two-person rule, where you need to have 2 authorizations out of a group of N people in order to unlock the data. And so we built a server here called Red October and helped use this, and this actually became a core part of Cloudflare that we've been trying to get rid of ever since. Luckily, we're getting close to the end of life on this, but it was very useful at the time. The other idea here is just to upgrade the software to do replication. But this introduced additional complications, particularly that of key management and that of trust. And so if you are going to have services talking to each other using TLS, you need to build your own certificate authority and manage your own certificates and these sort of things. And this is something that well-established companies knew how to do, but we sort of had to bootstrap this because we were so short of resources and so small. So effectively, what we ended up building was an open source PKI toolkit that allows you to build certificate authorities, build certificate authority chains, sign certificates, and do this, that, and the other. And as was our want, and as what we tend to do, is this was not something that was secret and proprietary to Cloudflare. This is something that implements public protocols. So this was open sourced. And so this problem was solved, and solved pretty quickly. But as a follow-up, we had new policies that knew anything internal to Cloudflare data sent over the internet is now mandatory to be encrypted. CFSSL was actually ended up being used as a core part of services like Kubernetes or Let's Encrypt, which is a free public certificate authority. And some lessons here is that PKI itself is relatively difficult to automate and adds a lot of complexity to the system. And this can be highlighted by this recent failure that happened at Ericsson. Certificates expired, and all sorts of cell phones went offline. This is something that happened regularly at Cloudflare. Managing automation and managing the ability to change your certificates and keys in a way that doesn't cause operational outages is actually very, very difficult because of the way that technology evolves. So in any case, moving on to the next story, this is at the same time that we were building this end-to-end encrypted as well as point-to-point encrypted system for distributing SSL private keys. Something else happened around 2014 when we were building this. So specifically, the Heartbleed bug. And if folks remember this, I can go into a little bit of detail of how this worked. But this was a bug in a piece of software, OpenSSL, that was used at the time 50% of websites on the internet. And so this was an information leak, but a sort of insidious one, because it was in the process that handles the encryption and decryption of data. This was discovered independently by two groups. It was disclosed to us and a few other parties early in sort of this type of exchange. Do you use TLS heartbeats? What's a heartbeat? Oh, they're this pointless thing that you don't need. They're disabled. They're enabled by default in OpenSSL. You should probably disable them. OK, we'll disable them. That was the disclosure. Probably should have thought more into this before it happened, but we didn't want to ask too many questions. So in any case, this is the timeline between when we patched and a week later it was publicly disclosed, and obviously this became a very big deal. This is me on CNBC trying to explain the issue. But we thought it was a small bug. Turns out it wasn't. Specifically, what would happen is you could take a buffer and give a larger, a heartbeat is this protocol in TLS that allows you to see if the server's alive. So you say, hey server, send me back X bytes. And if you pick X to be larger than the size of this response, you can get random data that's just sitting along in the server's memory. And that can potentially include previous requests and cookies and all these sort of things. And so, but the question, when it first was announced, it wasn't clear to the world, particularly, can you get private keys out of something like Nginx that uses OpenSSL? And particularly our co-founder, Lee Holloway here, found it particularly annoying to have to think about, hey, should I really spend a week or two with this rusty system that we built up to renew every single certificate for all of the customers that were using Cloudflare at the time with SSL? And he sort of put out a challenge saying, well, if you can show me that you can get private keys out of here, then I guess I'm going to have to do the work. And so this raised the question, can we actually get private keys through Heartbleed? Obviously, we all know the answer now, but at the time when this was first announced, it wasn't clear. And then the secondary question is, should we revoke these certificates? And then how do we prevent this from happening in the future? And so the result of these sort of problem statements, these research questions, we went to a tool that works really well in solving hard problems that are binary in terms of 1 and 0. And we built a challenge. This is the Cloudflare Heartbleed Challenge. And this was a website that was intentionally vulnerable to OpenSSL Heartbleed. And it had a form that said, if you can figure out the private key, then sign this value with the private key, and you win the challenge. And you get a T-shirt or something like that. But it was very popular at the time. And people did find sort of issues with the implementation itself. The funny part about Heartbleed is that it gets you memory that's listed on the stack. And so if someone were to submit a fake response that contains something that looked like a private key, some other person who's exploiting Heartbleed might see this, and it ended up happening. People started polluting our memory space with fun stuff. But within less than a day, the challenge was solved. First on Twitter, someone announced, hey, I have the private key, and this is us at the time verifying it. The power of the crowd is humongous for specific things like this. I mean, we spent a couple hours trying to extract the private key and weren't able to. But in 48 hours, 25 different people from around the globe came about and were able to extract the private key. They used mathematical tricks like the coppersmith trick, and keys were definitely vulnerable. So this was the result. And as I mentioned, Lee was not very happy about having to revoke and reissue these keys, but we had to do it anyway. And this led to a problem of scale that the internet had not necessarily faced. This is a heavy metal logo for revocation to make it seem scary. But in any case, we had 100,000 certificates that we were managing at the time, and we, on April 16th and 17th, decided to revoke all of these certificates to see what would happen. So it was very, very soon after the Cloudflare challenge. And revoking these certificates did not have a very smooth effect on our infrastructure. In particular, the tool to indicate to clients that a certificate is revoked is something called a certificate revocation list, which is essentially a signed list of serial numbers. And if you revoke 100,000 certificates in a day, this is not something that's usual. So the CRL for GlobalSign, the CA we were using, grew from a couple kilobytes to over around 5 megabytes or so. And because we were actually the CDN that was serving this, this started causing operational issues. We started seeing these waves of traffic every 3 hours or so from different clients that would request this massive, massive piece of content, and it would congest our inner caching mechanisms in the network. This was something massive, and it's not super clear that it provided a ton of value. So this was effectively a DOS against Cloudflare itself. So with CRL, it was clear this is not actually thought through to be something that would scale to internet scale. And so there's another revocation method called OCSP, which is a query response mechanism. You see a certificate, and then you query an OCSP server and say, is this revoked or not? And it says yes or no. Well, it turns out that OCSP was not something that, first of all, it wasn't enabled in some browsers. And there were multiple other issues with this, including privacy leaks involved with OCSP. OCSP was also turned out to not be something that was completely well thought through. And this led to some research as well as practice. From the practice side, there's a newer technique called OCSP stapling, which allows you to take the OCSP response and put it into the handshake itself and send it down with the certificate. And we, with collaborators, measured the internet for how ready it was for this OCSP stapling mechanism and how ready it would be to accept certificates that required this. And it turns out it was very rough. There were so many issues, so many bugs. It's almost as if this mechanism was never really relied on. In any case, how we ended up revoking all of these certificates in Chrome, which didn't do OCSP, didn't do CRLs, they had their own thing called CRL sets, was we wrote this 3-line patch that just explicitly revoked Cloudflare's certificates from the time of Heartbleed until anything that happened before we patched for Heartbleed. So this is very efficient, but it's also not something that scales, and it's not something that is necessarily works for everybody. It works for a centralized place, but not necessarily for everybody. You can't write code for every website. Heartbleed was fun. It was an exciting, interesting time, and we learned a lot about how the systems that we had built, we, as in the broader internet community, with respect to PKI, were not necessarily fit for the scale that they were being operated at. So we had some follow-up questions here. Reducing the lifetime of certificates is one way to help make this revocation problem go away. And then also, how do we keep the keys out of this memory space in the first place? So we also had some interesting issues around performance, all sorts of different things that came out from this. But it was a really interesting time. So as a small company, we had a lot of things going on. And so meanwhile, in London, John Graham Cumming, who's the CTO of the company, and I were working on another project that turned out to overlap with some of the problem statements of, or some of the potential avenues to investigate after Heartbleed. And that, in particular, we had a set of customers, financial services customers, who were not willing to share private keys with Cloudflare. And so the question is, at this point, how do we terminate TLS without having the private keys. And this led to some pretty interesting designs. First of all, about splitting up the TLS handshake, and then how do we actually practically do this with a short amount of time and 1 or 2 engineers at our disposal to do this. And so this was a very fertile ground for research. We wrote a paper here with Douglas Stabila about something that was able to take the key and separate it from the TLS handshake. So you could imagine doing cryptography. There's various different portions of a mechanism for establishing a key. There's a key exchange algorithm, there's a cipher that you choose, and there's a private key operation. Well, what this does is you just take the private key operation and you move it to a remote server. We called it keyless SSL. It's not necessarily a brand new idea, but the implementation and the deployment was. So effectively, this allowed financial services companies to allow Cloudflare to terminate their TLS traffic and inspect it and do caching and all these great things, while still not having access to the private key. And they could revoke access at any time. It was only accessible via a signing, what turned out to be a signing oracle, which was subject of further research, let's say. So keyless SSL came out, and this was something that was useful for certain large customers. And somebody asked on Twitter, is this potentially a pattern that could be used for Cloudflare while expanding our servers from what I think at the time was maybe 50 data centers to what it is now about 190 or so. And so this is the CEO, Matthew Prince, tweeting in 2014, yup. And so that is what we did. We actually leveraged keyless to expand Cloudflare's service into China, specifically here by keeping the private keys outside and terminating traffic inside, unless the users would choose to put their keys inside of Chinese data centers. It was also expanded to a project called GeoKey Manager, in which I did a presentation about this at Real World Crypto. Again, it's a little bit faint there, but this basically allows users to choose which regions of the world their keys are kept. So if you're sensitive about this, you can say everywhere in the US except for Virginia or something like this. And so GeoKey Manager is actually something that people use quite a lot. And it does have, along with everything keyless SSL, this latency problem, where the very first time you connect, you actually have to do this remote call. And if the key is kept in another country, this is additional latency. And this slows down your handshake. This is something that really will hold back the technology long term. But it did lead us to 2 new avenues of research. And one first is solving this problem that was originally raised with Heartbleed, is how do we keep the keys out of the memory space? Well, you just put your key server in the same data center as your TLS terminating server. And if you have a memory leak on the edge that's actually doing the TLS termination, you don't have the private key leak. So this was called a project called Going Keyless Everywhere, where we transitioned our entire network to using this architecture. The latency problem was more difficult. One of the fun parts of keyless SSL is this is a server-side only change. It doesn't change the fundamental protocol. It's just something that we do to refactor where pieces are sitting. So how do you solve the latency problem? Yeah, it's basically here. You have a web server app and your key server, and this adds latency. Well, after talking about this with other folks who had similar constructions, we found that one way to do this would be to, rather than using the long-term private key to sign the transaction itself, you could sign a short-lived delegation key. And this became something called delegated credentials. This is an IETF draft. It's moving through. It's on its way to becoming RFC. And essentially how this works is, out of band, you get these short-lived keys, and they get signed by the key server. And this is what's used to sign TLS connections. So you don't actually have to go back to the key server every time someone does a connection. You just use the short-lived keys. So with this, our keyless SSL journey is mostly over. And so I mentioned at Cloudflare, I sort of told some of the inside stories of these technologies that help encryption grow, at least with respect to what we have. But this talk is more about the internet itself. And in particular, you remember what I put a pin in, which was the websites that didn't use HTTPS back in 2014. Well, this was the norm. It was less than 30% of connections were encrypted with HTTPS at the time. And of the Alexa top million sites, less than 10% supported HTTPS. And in terms of the underlying protocols that make HTTPS encrypted web browsing work, TLS 1.2 was just being rolled out. And so we had a goal, and this goal was shared by many industry partners and something that was helped push along in that era, of boosting HTTPS adoption globally, because a lot of what everyone does online goes through these major websites. Browsers helped by first announcing that they would be deprecating non-secure HTTP. This is obviously something that's happened. If you open up HTTP sites in either Chrome and Firefox now, it will mark it as insecure. But at the time, this was not possible to do immediately. You had to get to a point in which users wouldn't be scared of this, or users wouldn't have to see a not secure and think something else is going on. We had to get to a point in which most of the web and most of the sites that people usually see are encrypted with HTTPS. And so our first goal was, well, how can we help? How can we help this? And the first goal for us was to enable TLS, by default certificates, for Cloudflare's, what was at the time, 2 million customers. At the time, it was only Cloudflare's paid customers. As I mentioned, there was only 200,000 certificates that we revoked for Heartbleed. So after this, we sat down and sort of thought, like, how can we scale this? How can we go to encrypting all of these different customers in a way that our system can handle? One problem was IP addresses. At the time, and sort of earlier on in the internet, one IP address corresponded with one server. And this was definitely not the case anymore. And specifically, Cloudflare did not have enough IP addresses as a new company to be able to serve an individual IP address for every customer. So you can put 20 customers on one IP address. Well, you can, if you're not using encryption, you can put 1 million customers on the same IP address. You just look at the header that says host, and then you route the traffic that way. When it's encrypted, you have to be able to, given an inbound connection, use a specific certificate. So you can put multiple customers on one certificate. And the problem here is that we had this cluster of IP addresses that had 400 or so customers on it. And putting 400 or so names into one certificate was beyond the technical means of what browsers were expecting. It would slow things down too much. And so the solution to this issue of not having enough IP addresses was really to limit the number, the actual functionality. Specifically, we required customers or visitors to these sites to use what is called SNI, server name indication. It's a plain text extension that says, this is what the host name is, I want to connect to it, et cetera, et cetera. You could still keep 20 plus customers on the certificates, and this was being rolled out. So this helps kind of solve this issue to one extent or not. You can put all your customers behind one IP address if you want, as long as you have SNI. And so what was the other problem? Well, I don't think I mentioned this before, but I should have, but RSA is slow and expensive. And that was the only certificate type that our partners support. And at the time, nobody on the internet was using elliptic curves for cryptography for certificates. In fact, it was only, I believe, Gmail or some Google properties that used ECDSA certificates at the time. And not all browsers supported it, because it was relatively new. Although elliptic curves have been around since the 80s, in terms of actually practically defining them in protocols, it took a lot longer. So it was fast, though. We had this fast implementation by Shai Garon and Vlad Krasnov to make elliptic curve ECDSA 50 times faster. And so, yeah, these two problem sets kind of overlapped. You had a set of clients that didn't support SNI, and you had a set of clients that didn't support ECDSA. And we decided to enable TLS for every single one of our customers, but require that the browser was mature enough or modern enough to support both SNI and ECDSA, which at the time was around 90-some% of the internet. And so as old browsers got phased out, then this became more and more feasible for people to use. So we launched in 2014. And when we launched, millions of more sites gained HTTPS. I think at the time, it was calculated that we doubled the size of the encrypted web. One sort of interesting tidbit here is that the lava lamp wall itself was slightly inspired by our choice to use ECDSA, which is vulnerable to bad randomness. So in any case, this all sort of ties around from that. And so with encrypted SSL, or sorry, universal SSL, this has continued to scale. It took about 10 or so days for us to issue enough certificates for this to work. But now we're up to tens of millions of certificates and maybe 100 million by the end of 2020, which is sort of moving things along. But at the same time, this was just at Cloudflare. A project called Let's Encrypt was launched 2 years later. It was being incubated at the time. And this allows short-lived certificates for free, and it is in part powered by CFSSL, something that came about during our own initial problems with setting up an internal PKI. So this was a good synergy, if you will. But having certificates, we're talking about encrypting the internet, having a certificate is not enough. That basically fulfills the bare minimum qualification of, do you have this port open and a certificate? And is the certificate current and valid for this domain? The further you go down this list of requirements, the better your site is with respect to encryption. At the very bottom here is, are you on the HSTS preload list, which is essentially a white list of sites that is known to be guaranteed to always be accessible over the encrypted protocol. And sort of moving people down, this was the subject to subsequent features. So there's HSTS headers, there's redirects, there's automatic rewrites, leveraging things like the EFF's list. And this helped eliminate things like mixed content that helped sites get to 100% HTTPS. And so after this and our contribution, we sort of asked ourselves, well, is the internet encrypted yet? I mean, and looking at this from 2019, as an industry-wide push, this has been relatively successful. The stats are from Chrome that something of 80% of page views are now HTTPS. And in terms of redirecting from HTTPS, it used to be less than 2%, and now it's 40%. So you can see this is from 2015 onward and various countries, how this has gone. So this is great. I mean, the internet is encrypted, right, with TLS. But yeah, in the meantime, this was a very fertile time for researchers in the academic crypto community to take a look at TLS, the protocol that was being used, and rip it to shreds. You may recognize some of these vulnerabilities. Some of you may have written these vulnerabilities or discovered them yourselves. And so from the time that we were encrypting the internet, all of these other problems with the protocol we're using to encrypt the internet were cropping up and showing up. Things from breach to Lucky 13, freak, sloth, drown, robot, all these sort of things. Some of them are even too new for this slide. And what we were essentially doing was patching the problems. This is, for example, after the RC4 vulnerabilities were announced, we made the switch to remove RC4 as a cipher. And then this actually brought back this triple DES as a form of encryption on the web. And that was also subsequently broken with the Suite 32 attack. So in any case, we were just patching problems. And TLS looked like this. This complicated takeout menu with a lot of different letter salads, and people didn't know how to contribute it. And what we really needed was something like a prefix menu, something easier to analyze formally and with proofs and nasty things like non-forward secret ciphers removed. So back to on the internet, our rallying cry here was let's encrypt the internet, but it really should have been let's encrypt the internet well. And this is where TLS 1.3 comes into play. Upgrading an ecosystem like the web is really, really complicated. There's a lot of different parties involved. Servers, clients, and this whole hidden array of network middle boxes and network appliances. And so TLS 1.2, as I mentioned, was just being deployed back in 2013. That was 5 years after it was standardized. And so it took a very long time for this to be deployed and to be standardized. And the pattern in which this went was it was specified, and then it was deployed, and then problems happened that were measured on the small-scale deployment, and then things had to adjust. And because the specification was almost already finished, this adjustment couldn't come in the spec itself. It had to come through things like calling up server operators at Yahoo and saying, can you please change your cipher suites? Or, hey, your system is not compatible with 1.2, can you please fix it? Even though in the spec, everything is meant to be forward and backwards compatible. So TLS 1.3 was started around the same time that most of these stories started, back in 2013, 2014. And the benefits are that it's faster, so one fewer round trip to set up. There are fewer choices and better choices for things like ciphers, key exchange algorithms, all signature algorithms, everything, all the different pieces that you can combine together. And it was required to be formally verified, which is part of how a lot of these attacks were discovered, was through actually attempting to formally verify TLS 1.2 and failing. And so the pattern for TLS 1.3 was to specify, do some deployment, do some measurement, and then adjust by changing the spec. And by having this entire wheel together, you could actually end up with a much, much stronger protocol. And so how did we fit into this? How did we help? Well, as I mentioned, Cloudflare has this sort of architecture with traffic comes in, it gets proxied, and then goes out. What we did was, it was very difficult to actually modify OpenSSL and change OpenSSL to support these different iterations of the draft. So the first iteration of TLS 1.3, I think, was something like 2015 or so, and they went through dozens of different versions until the final one was developed. So what we did was we took a prototyping language called Go, and we built our own stack, and we took every handshake that was supposed to be TLS 1.3 and sent it to this new stack. And this allowed us to iterate much more quickly without affecting existing customers. And we weren't the only ones able to do this. Facebook, as well as Gmail, they had rapid iteration cycles on their implementations, as well as Chrome and Firefox had the ability to deploy into beta and canary versions of their protocols, of their browsers. So these, in conjunction, all spoke TLS 1.3, or could, at least until the browsers turned them on by default. So in October 2016, Firefox Nightly turned on their, whatever was the current version of TLS 1.3 at the time, and then Chrome Canary did the same. And this is from our side, because we had supported TLS 1.3 at the time. And so this was very interesting. This was actually, we started seeing connections, things started to come through, and we were able to analyze to see whether or not this protocol actually worked. And if you fast forward to February, you'll see that TLS 1.3 did not get finished and did not get turned on. And you may think that it was because of, you may have heard of political questions about this. I mean, having a protocol being developed for so long, you have people learn about it, especially people with different requirements. So for example, I mentioned having no non-forward secret cipher suites. There's one based on RSA key exchange that was in TLS forever. Certain banks, financial institutions said, no, we need this in the protocol, otherwise we can't do out-of-band encryption. And the IETF, this is specifically, Kenny Patterson sent this reply saying, my view concerning your request, no rationale, we're trying to build a more secure internet. And so, but this wasn't the reason. This doesn't actually hold back TLS. It was an example of standards bodies sort of holding their ground to architectural purity or security features that are very necessary and that were informed by the understanding that TLS keys were being massively collected and decryption was happening. So in any case, this was sort of a rough year. I'm trying to find some bright spots, but eventually in 2017, the reason that it wasn't deployed was revealed, and this was in particular, it was middle boxes. This idea of these services that sit on the network, inspect traffic, and they've sort of grown used to what TLS looks like over the years. So they're expecting specific functions or specific messages to look a certain way, and started failing in odd ways once it's been upgraded to TLS 1.3, to the point where more than 1% of connections were just failing across the world. Simultaneously, we were doing a study led by Zakir Jarumich and others on how pervasive this is, and we found that the idea of just having a TLS terminating middle box was upwards of 10 to 15% of all traffic is actually not end-to-end between the browser and the server. It goes through some sort of interception inside of some data center. Usually someone installs a root for an enterprise system. In any case, this was very prevalent and caused TLS 1.3 to not be able to be deployed because it would fail. And these things are very hard to update, but they're very hard to account for. And so Adam Langley from Google came up with this, this is paraphrasing him, but this philosophy that kind of explained how we had to make changes to TLS to, rather than force the middle boxes to change in order to accommodate TLS. And that's the idea that the last chance change is always to blame. So even if TLS 1.2 is specified to be forwards compatible and everyone has followed the spec as close as they can, but if things are deployed and they're deployed incorrectly, you make a change and you cause that defect to be exposed, it's your fault. And so this is kind of one of the big lessons of TLS 1.3. The philosophy around the solution to this was this idea called GREASE, which is generate random extensions and sustain extensibility, which is David Benjamin, an engineer at Google, came up with. But the idea is to force these middle boxes to understand that the protocol can potentially change. So you send random versions that are for different cipher suites or for different things that the server should ignore. And so, for example, one of the main reasons TLS 1.3 didn't work out of the box was the version number. It sent 1.3, and the logic is if you see 1.3 and you support 1.2, then you just answer back with 1.2. But all sorts of servers were failing. So sending future versions is one of those things that can safeguard us from any ossification that were to happen in these network protocols. So the last chance is always to blame. When TLS 1.3 is deployed, if it's greased, then the middle boxes will be the ones that make the breaking change, and they'll be forced to fix it earlier, or at least that's how it comes about. Okay, so stepping back a bit, TLS 1.3, we're kind of in the weeds. It was standardized in 2018, and this is what it looks like in December. I'm happy to show here that from Cloudflare's perspective, sorry, the colors don't match, but TLS 1.3 here is the red portion. So we're coming up on 50% of encrypted web traffic using TLS 1.3. So that's really cool. That's kind of an interesting final thought on this. If you compare this to TLS 1.2, which took 6 or 7 or 8 years even to get close to this level of deployment. So rapid iteration and thinking about the problem in strategic ways, doing research really helps. Okay, so I don't have a lot of time left. I guess I do have a lot of time left, but we can ask some questions. But I have some other things we can go into if folks are interested, but it's the end of a long day. But some of the follow-up research problems that were highlighted by this work is the idea, first, of beyond the first hop. So the browser can really only show you so much and really only know so much. If it connects to a website, it shows a proper certificate. You can get that nice little lock icon or purse or whatever it is, and demonstrate that. But the browser doesn't have any visibility as to what happens when the traffic is sent beyond that first hop. And so for something like Cloudflare, we have the private keys, or we have the proxy for the private keys using keyless SSL, and that connection is end-to-end encrypted between the browser and Cloudflare. What about Cloudflare to the origin? Or what about various other hops that happen along the way? How can we be assured that these sort of things are being encrypted? This is still an open problem, and it's very difficult to explain to users and to show them in a realistic way what happens beyond the first hop. So that's one problem. Another one, which is a hotbed item right now, is encrypted DNS. I mentioned how we've gotten to 80% plus encrypted HTTP. DNS is the phone book of the internet. It's the metadata of which websites you're going to. This is not encrypted, but there's been recent protocols proposed for encrypting this using TLS in much the same way that HTTPS is encrypted, by putting it in an encrypted tunnel. There's some definitely interesting deployment challenges with this. It's been relied upon in ways much more complicated than the plain text TLS structure has been relied upon by network applications and especially for things like threat detection, et cetera. The follow-up to this is encrypted SNI. I mentioned how we were able to scale to massive numbers of sites behind one IP address using this indicator called SNI. Well, SNI is sent in the first flight, so it has to be unencrypted. SNI contains the host name of what you're going to. So this is essentially as much of a data leak as DNS is. And so finding out the right way to integrate SNI encryption into TLS is actually turning out to be more difficult than originally thought. So there are some interesting engineering challenges to do with that as well. Following up, post-quantum security. I think we all know that there's some concern around this going forward. Post-quantum encryption algorithms do not have the same shape as the ones currently used in TLS. For example, there's no Diffie-Hellman analogous algorithm in terms of key exchange in post-quantum. So this is another area that is actively being explored. And the very last one here is something that is a linchpin for all of the encryption online, and something that I sort of hinted at before when talking about short-lived certificates and even OCSP stapling. In order to trust a short-lived certificate, your clock has to be correctly synchronized. And this is not something that is happening on the internet to a high enough degree that it's safe to roll out short-lived certificates and short-lived things like OCSP stapled responses. So secure time synchronization and making sure that all these applications, these devices that are attached to the internet actually know what the right time is another sort of very active area of research. Okay, so takeaways from this talk. The internet is not yet encrypted, but we're trying. We've gone quite a long ways on HTTPS, and also taking TLS and turning it into a protocol that has much more stronger assurances about it and is widely deployed. And internal hard problems that are sort of practical day-to-day problems with engineering actually can yield interesting research avenues, and these sort of things can feed on them on each other and contribute to some pretty interesting innovations. And finally, research work can be superpowered in a way when combined with this iteration and deployment of real-life systems at scale. So this is one of the lessons of TLS 1.3. Okay, so with that, I'd like to thank the audience and open it up for questions. Thanks.